Hi guys, welcome back to my channel. Today we're doing an induction proof. So let's just jump right into the example, which is prove by using mathematical induction that 2 to the power of 0 plus 2 to the power of 1 dot 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 all the way up to 2 to the power of n minus 1 equals 2 to the power of n minus 1 for all n greater than or equal to 1. So for induction, for our induction solution, we'll need two things. We'll need a base case and our inductive hypothesis. So the first step is finding the base case, which is usually you set n to 1. And using that, we look at our original equation from the problem, which was this. And then we examine where n is equal to 1. So our first term is n equals 1, second term is n equals 2, third is n equals 3, dot dot dot, all the way to n equals n. So looking at this, we see that when n equals 1, we have 2 to the 0. So that would be our n equals 1 element. So we take that, so when n equals 1, our left hand side is 2 to the 0, which is equal to our right hand side, where we just replace the n with a 1. Simple. And then we simplify and simplify, and we get 2 to the 0 equals 2 minus 1, which is equal to 1 equals 1, which is a true statement. And since we have a true statement, this means the conjecture holds for the base case when n equals 1. Okay, so now that our base case is done, and we can now move on to our second part, which is the induction part. So for induction, instead of looking at like a small value, we want to be looking at an arbitrary value. In this case, we'll call it k, so we'll say n equals k, and then we'll substitute all the n's in the original equation with k's. So we'll have 2 to the 0, 2 to the 1, dot dot dot, 2 to the k minus 1 equals 2 to the k minus 1, and we'll call that equation 1. Now we want to prove the conjecture for an even greater value than k, so k plus 1. And to do that, we also will want to substitute all the n values with k plus 1 from the original equation. We want to prove that this is true right here. We want to prove that 2 to the 0 plus 2 to the 1 all the way to 2 to the k minus 1 plus 2 to the k plus 1 minus 1 equals 2 to the k plus 1 minus 1. So this equation right here is essentially when you take k plus 1, we take this new n value, k plus 1, and we plug it in, and this is what we should get. We want to prove that this is true. And we'll call this right hand side right here equation 2. So to prove it, we just take this equation, and then we notice that something special happens on the left hand side. We notice that the first set of values all the way up till k2 to the k minus 1 is actually equation 1 that we established earlier, and equation 1 is equal to 2k minus 1. So using this, we can simplify the whole thing to 2k minus 1 plus 2k. And we get this 2k from this part. So 2k plus 1 minus 1 is equal to 2k. That's how we get that 2k. So the right hand side becomes this, 2k minus 1 plus 2k, and we keep simplifying. We put these two k's together, and we get 2 times 2k minus 1. And then we know that this equals 2 times 2k is also equal to 2 to the 1 times 2 to the k minus 1. And that equals, and this equals 2 to the k plus 1 minus 1. And we call this equation 3. Now that we have this, we notice that it is equal to equation 2, which is up here. This is equation 2, and this is equation 3. So we now see that because equation 2 is equal to equation 3, the conjecture holds for n equals k plus 1. Now we can proudly say that 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way to 2 to the n minus 1 equals 2 to the n minus 1 for all n is greater than or equal to 1. And QED just means it's been proved. So we have thus proven this using induction.